Okay, so today we have two topics called phase changes and latent heat. And I'm sure you've seen the beginning part of phase changes before, probably even in primary school. But today we're going to elevate that knowledge into a high school level and unite it with what we saw last class on thermal equilibrium. So the basic starting point, to which you definitely should already know, is that there are three basic phases of matter. There are others that we're not going to talk about here because we only care about these three basic phases, and those are solids, liquids, and gases. And actually, because this topic can get a little complicated, we're only going to talk about water. So everything we're going to do today is just talking about water, but changing the numbers. This information can all be transferred into any other material because every material goes through the same phase changes, just at different temperatures and requiring different amounts of heat. So I put here 6 words that define changes between solids, liquids, and gases in all directions. Some of them skipping steps and some of them going like in this direction or in this direction without skipping steps. So you know most of them, but just in case, I want to make this list so that you have it. It's going to be useful in a second. So fusion. Fusion is when you have ice and it melts. So again, we're talking about water. So you have ice and it becomes liquid water. And when I say water here, I'm talking about liquid because that's what we usually call water. And I'm going to call ice the solid version of water and vapor or steam the gas version of water. So from ice to water, melting is called fusion. Vaporization or vaporization is from water to vapor. That's why it's called vaporization. Sublimation is directly from ice to vapor, skipping liquid water. So if it skips the middle step, it's called sublimation. And then going in the other direction, we have condensation, which is when you have vapor and you go to water. So it's the opposite of vaporization. Solidification is when you have water and you go to ice. So the opposite of fusion or melting. And deposition is when you skip water again and go directly from vapor to ice. So skipping the opposite of sublimation. So from vapor to ice. So these are the 6 changes that can take place from solids to liquids to gases or the other way around. And they have their specific names. Today we're going to focus on 2 specific ones, which are fusion and vaporization. And they're opposites, but we're going to use these 2 words for everything that we're going to see from now on. So make sure you have this in your notes. It's going to be useful, but I'm going to erase it right now to show you where I want to take this. So let's see. I'm going to make a graph. This is a graph of temperature versus heat energy that I put into it. So this is temperature in degrees Celsius, and this is heat input in joules. Okay, and this scale, this is 0 degrees Celsius. This is -20, -40, 20, 40, 60, 80, 100. And it doesn't fit, but here, let me do it a little bit bigger. Let's get to at least 120. Okay, temperature in Celsius. Perfect. So what I'm going to be showing you guys here is what happens when you have a mixture of ice or water or vapor, and you put some heat into it. So this can be exemplified in real life as putting a pot on your stove, turning on the stove, and putting first just a piece of ice and seeing it melt or seeing it go through the different phase changes. So suppose we have that example. So I'm going to give each of you a block of ice at a temperature of negative 40 degrees Celsius. So it's really cold. And this is the beginning of our experiment. We haven't put any heat to it. We just have a giant block of ice that is very, very cold. I'm going to give it to you. You're going to put it inside a pot and you're going to put it on your stove and turn on the stove. So what you're going to do is start putting heat into it, giving it some heat, some energy. So the first thing that's going to happen, as you can probably imagine, is that the ice is going to start getting warmer. It used to be at negative 40 degrees Celsius and it'll start warming up because everything below zero is still frozen. So you can have ice at negative 5 or you can have ice at negative 40. So until you get to those 0 degrees, the ice is just going to become hotter ice that isn't as cold as before. So the graph is going to look something like this. So you add heat to it and it gets hotter until it gets to 0. But what happens when it gets to 0? We know that at 0 degrees, water freezes or ice melts. Right? So both things that happen at 0 degrees, because 0 is the freezing point of water. So if you had water, you put it to 0, it freezes. If you had ice, after 0, above 0, it melts. So at 0, definitely something is going to happen. So what surprises most people here is that this graph isn't going to be a straight line upwards because something happens here. So you have ice and you want to make it water. And for that you need energy. Because if you remember, the molecules in ice are stuck together. The molecules are very close to one another, forming this crystal, this lattice structure of molecules stuck together. And you need them to become water so that they don't have as strong intermolecular bonds. So what we need to do is that we put energy into it, and the energy, instead of heating up the ice any further, it's going to melt the ice. So the temperature is not going to increase for a while because this is going to look something like this. Because there's a period in which we keep putting heat into it, and that's why the line keeps going to the right, but the temperature is going to stay at 0 as the ice melts. Right? So when the ice finishes the melting process and now all of it is water, then again heat can stop being used to break the bonds between molecules and can start being used to elevate the temperature of water again. So now the water is going to heat up the same way as the ice did as you put more heat into it. So again we're going to have a diagonal line. Until when? Until we reach 100 degrees Celsius. So let's see, 100 degrees. Sure, it's about, I was almost there. So why? Because as we know, as we learned before, 100 degrees is the temperature at which water becomes vapor, or at which vapor becomes water. So at that point, there's going to be another phase change, and the same thing is going to happen. So water still has some bonds between molecules, and they're still sort of stuck together, even though they can flow more freely than in ice. But vapor doesn't. In vapor, the molecules are very, very far apart, and they're moving a lot quicker. So you want to make them move quicker and be farther apart, and for that they need energy. So again, for a while, the line isn't going to keep growing. It's going to stay like this as all of the water becomes vapor. So all of the heat that you put into it, you have your stove turned on, you're giving it heat constantly, but it's not being used to elevate the temperature, it's being used to transform or to change the phase of the water into vapor. As soon as all of the water has been turned into vapor, and usually this takes a little longer than for all the ice to be turned into water, again, this vapor is going to be heated. So for the rest of the temperatures possible, the heat is going to be used to elevate the temperature because you're already at vapor, which is our third and final state of water. So basically, when you are here in this portion of the graph that lies between negative infinity to 0, you only have ice, and what you're doing is heating up ice. So this line here is just ice, right? When you get to 0, some of the ice will start melting, and you'll have a mixture of ice and water. So this is ice plus water. And something that people usually have a tough time understanding or accepting is that always when you have a mixture of ice and water, it's at 0 degrees. You can't have ice and water below 0, and you can't have ice and water above 0, because if it's above 0, all of it has to be water. If it's below 0, all of it has to be ice. So the only temperature at which they coincide and they can live together in a mixture is 0 degrees. So that's important in general. Okay, so once all of the water melts, then it can start increasing temperature. So this whole section of the graph is just water. Water by itself being heated up and its temperature increasing as you put more and more heat into it. When you reach 100, then water and vapor will coexist. Water and vapor will coexist in this section. So the same thing happens as with ice. So this section is going to be vapor only. So if you have a mixture of water and vapor, if you have water that's boiling on your stove, it's always going to be at 100 at sea level, of course. Remember, I told you here in Bogota, the boiling point of water is closer to 80 degrees Celsius. So maybe it's going to be the same graph, but down here instead, like this, right? Because this point is going to be reached lower. But we're doing this at sea level just because it's what you're going to find online and it's what we memorize. But of course it depends on where you're at, as we saw before. But basically, theoretically, the way we're going to be doing it here is that you can only have a mixture of water and vapor at 100 degrees. If you have only vapor, it's because you're above 100. If you have only water, it's because you're between 0 and 100. So that is the important part here. So what we learned last class about thermoequilibrium required some heat that we called Q. So I'm going to remind you guys the equation here. The equation was Q equals M times C times delta T. And what happened was that when you put heat into it, the temperature changed. So what this tells us is that this equation is only valid when we are in one of these 3 periods in which temperature is changing when you put heat into it. But in this case, no matter how much heat you put into it, if you are in this section of the graph, the temperature is going to stay still. So this change in temperature is 0. There is no change in temperature here or here. So this Q equals MC delta T, that works for this section, it works for this section, and it works for this section. That's where we use that equation. But if we happen to have a situation in which we pass through a phase change, like here or here, we need to use a new equation. So that's the equation that I'm going to teach you today. Let me use the orange. So this new equation also tells us what happens with heat, but now the temperature isn't going to change. So we don't need a temperature. Actually, this equation is very simple. It's M times L. That's it. M times L. So M is the mass, and L is called latent heat. So that's what gives the title to this unit. So M is the mass, and L is latent heat. So what is latent heat? It's a constant. Just like our C was a constant that told us how much each type of material requires of heat to change its temperature, L is also a constant. So because we're only going to talk about water, we only need two constants. So there is one that is called LF for fusion, and that is called latent heat of fusion. And there's another one that we call LV, which is the latent heat of vaporization. Vaporization. So we use that one for, so we use those two for this portion of the graph and this portion of the graph. So we saw that fusion was when ice melted and became water. So that means that we're going to use the latent heat of fusion when we're talking about this part of the graph, latent heat of fusion. And when we're talking about this part of the graph, we're going to have to use the latent heat of vaporization because we're talking about water becoming vapor or vapor becoming water. So that's why we use the latent heat of vaporization. So basically this equation is the mass of water or ice or vapor that you have times L, but L can either be LV or LF. There's no such thing as just L. It's always either LV if you're here or LF if you're here. So in the next video, I'm going to put numbers into this, show you an example of water changing temperature and changing phase with numbers so that you can put this into practice.